In this video, we'll talk about the central limit theorem. We can compute confidence intervals computationally through simulation, but what if there was a way to compute confidence intervals directly using statistical theory? Regardless of the parent population distribution, the central limit theorem, or CLT, states that the sampling distribution of the sample mean converges to a normal distribution when the sample size is large enough and we sample with replacement. Mathematically, we can say that as n goes to infinity, the sampling distribution of the sample mean is approximately normal, with mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of n. Now, if the population is normal, the sample will be roughly normal as well. But suppose we have a population that is right-skewed, clearly not normal. If we take samples from this population, each sample will be inherently right-skewed from the population distribution. However, if the sample size is large enough, typically at least 30, the sampling distribution of the sample mean will be approximately normal. Isn't this cool? This doesn't rely on knowing anything about the shape of the population. We can apply the CLT in statistical inference, in particular when we're constructing confidence intervals. A confidence interval usually takes the form of some point estimate plus or minus some margin of error, which determines the width of the confidence interval. The margin of error is comprised of a critical value times the standard error. From the CLT, we can use the standard normal distribution to get our critical value, z 1 minus alpha over 2. To further explain this notation for the critical value of z 1 minus alpha over 2, it represents the value such that there's an area of alpha over 2 to the right and left of the positive and negative critical values, respectively. For example, for a 95% confidence level, alpha is 5%, and the critical value of 1.96 on the standard normal distribution has an area of 2.5% in each tail. Proportions are a special case of the sample mean, so the CLT can also be extended to consider proportions. If the number of successes and failures is sufficiently large, at least 10, we have that the sampling distribution of the sample proportion is approximately normally distributed, with the mean of the population proportion p and standard deviation of the square root of p times 1 minus p over n. Using this result, we can compute confidence intervals for the population proportion in a similar fashion by taking the sample proportion plus or minus a critical value from the standard normal distribution times the standard error. Let's see how we can apply the CLT. Suppose we had a random sample of 100 students in an intro data science class, and the proportion of them who passed the class was 0.9. Since the number of successes and failures are both at least 10, we can use the CLT to construct a confidence interval for the population proportion of students who passed. To compute a 95% confidence interval for the proportion, we take the sample proportion of 0.9 and add and subtract the margin of error, the critical value of 1.96 times the standard error. This gives us a range of plausible values, so we can be 95% confident that the proportion of students who passed intro data science at a certain university is between 84 and 96%. Now, we are using mathematically defined distributions instead of a simulation-based approach to calculate a plausible range of values around a population parameter.